Okay, good evening. My topic for tonight will be a discussion on alternating current machines, and we are now on lesson number 44. This will be a continuation of the discussion on three-phase transformers. Okay, let's proceed. The subject matter for tonight will be AC machines, lesson number 44. We are now on lesson number 44. We are almost done with transformers, so the next time around I might discuss the concepts of alternators. This is now the so-called power generation machine. Okay, AC machines, lesson number 44 for tonight. And the title of the topic will be Example Problem on Delta to Y Connection. So we will not get lost on the computation of delta to y or y to delta. I would like to present the example problem for tonight, plus the application of the derived equation the last time around, that is in the computation for the total power of a three-phase load. That is total power is square root of 3 times voltage line to line times the line current times power factor for a three-phase load transformers. So we will be solving a delta to y connection, okay, in relation to the formula that was derived the last time around, Pt equal to this equation here. Okay, I will try to read the problem. Three transformers connected delta on the primary and y on the secondary. Step the voltage down, so meaning to say the given configuration is a step down transformer. I think under the concept of delta to y, it is for stepping down transformer of voltages. It could be from the primary line going to the secondary line to step down the voltage 13,200 to a value of 460 volts. Okay, so the delta y connection is actually for stepping down. So the problem specifies that the configuration is a step down, meaning to say a high voltage on the primary will become a small voltage on the secondary if the configuration is a step down, voltage down, right? From 13,200 to 460. This is 13,200, we will step down this one to 460. Okay, step down the voltage down from 13,000 volts, 200 to 460, and deliver a 750 kVA load with a power factor of 0.8. So with this configuration, the connected load and secondary is a three-phase balance load. Total rating is 750 kVA, 0.8 power factor. There are 6 unknowns to solve this problem. The problem is asking for A, small letter A, the ratio of transformation. So this will now be an application of our knowledge on the concepts of the formulas involved for transformer. Number 2, the kVA and kilowatt of each transformer. Since the 3 transformers are actually 3, the problem is asking what will be the kVA that could be carried by each of them. kVA and kilowatt. Number 3, capital letter I with the subscript load, meaning if the three-phase load on the secondary is balanced three-phase. Okay? The problem is asking what will be I sub L. I sub L. Right? I sub L. And I sub L. The given load is 750 kVA, 0.8 power factor. That's number 3. Number 4, capital letter I with the subscript L, again with the subscript primary, meaning this should be the primary current primary line current primary line current, it's this, plus this, and this one. Number 5, IAs with the subscript phase, meaning the secondary phase current. Phase current is the current passing through the windings, right? So the current passing here, coming out here. Okay? Okay? The problem is asking for this phase current here. The last one is the capital letter I with the subscript P, again, phase value. If these are line currents on the primary, the phase current on the primary will be this one. Okay? Plus this one and this one. Actually, these two values here are different because the connection is delta. For the secondary side, there's no problem. The connection is just a series connection, right? So whatever current passing through the windings will be the same as the line currents going out. Okay? So with regards to the current on the secondary, there's no problem. Whatever current coming out from the windings, it will be the same as the line currents. It will be the same as the load currents. So with respect to the current, there is no problem on the secondary side. The connection is why. The problem here is on the primary, because the line currents are actually different from the phase current, right? This is bigger and this is smaller, right? Okay, let's try to bring out the solution. This will be the figure, right? The problem is asking for number 1, the ratio transformation. Okay? And using this formula, okay, the condition should that we shall be using phase values. Okay? Phase values. It's not the line values. So if you try to take the ratio of BP over BS, it should be the voltage across the windings. Okay, voltage across the windings for this to be correct. That's why I specify here using phase values. You cannot use the ratio of the line-to-line ratio voltages. It should be, for this formula to be correct, it should be BP over BS using phase values. So if you try to compute for A, it should be the voltage across this divided by the voltage across this. Okay, it should be the phase value. For the primary side, the line-to-line voltages are actually 13,200. But since the connection is delta, whatever line voltage that will come out, it will be the same as the phase voltage. So I place it here. On the primary side, the phase voltage is 13,200 also. The line-to-line voltage is 13,200, and since the connection is delta, the phase voltage should also be equal to 13,200. So if you try to substitute values here, we will use the 13,200. Okay. How about the secondary side? For the secondary side, the line-to-line voltages is 460. Okay, so the phase voltages will be less than the line-to-line voltages. And the relation of the line-to-line with respect to the phase voltage for a Y-connected transformer is actually given by this formula. Okay, that is the line-to-line voltage for a Y-connected is square root of 3 times voltage per phase. Okay, we are given BL 460. So if we try to compute for the voltage across its winding, it should be BL divided by square root of 3. So this is BL 460 Sorry for this one, this should be 460. It's not 400, 460. 460 over square root 3, so this should be 265.6 volts. Okay. So this is 265.6. This is 13,200. So if we try to compute for the ratio transformation, it should be step down, right? So it should be the ratio of this voltage here divided by the computed voltage per phase on the secondary. So this should be 13,200 over 265.6. And the ratio of transformation is 49.7. It is almost 50. Meaning to say, if you got 1,000 volts here on the primary, if it is a step down, you divide that by 50 times, so you will reduce that 10,000 to a certain voltage, which is lower than the primary voltage. That's why it is a delta to Y connection is actually for stepping down voltages from the transmission line going to the secondary side. So the answer for number 1 will be 49.7. Oh, this is now an application of the concepts of the, what they call this, equations involving transformers in relation to delta to Y connection or Y to delta connection, plus this formula here, that was the last time around. Okay, number 2. The problem is asking for kVA and kilowatt of each transformer. kVA is the apparent power, kilowatt is the total true power. So if we know kVA, we just multiply kVA by power factor, that will now be kilowatt. So in our computation here, the transformers are alike, they are the same, okay, and they should carry 750 kVA. So each winding will carry 1/3 of 750. So the kVA per transformer, because it is 3, right, should be, because the total load is 750. Since they are helping each other, the rating per transformer should be the total power delivered to the load divided by 3. So this 750 by 3. So the total apparent power that could be carried by per transformer or per winding is 250 kVA. For the kilowatt, it's just a conversion factor. Converting it to 50 times 0.8, because power factor is kVA or kilowatt over kVA, therefore kilowatt should be kVA times power factor, which is 200 kilowatts. Number 3, the total load is 750 kVA. What will be I sub L? The current coming out from the lines on the secondary, since the load is balanced, they are all the same, right? So if we try to compute for the value of I sub L, we'll just compute 1 and they are alike per each winding. So using the formula, the 1 we derived by using the 2 watt-hour method the last time around. That is capital letter P with the subscript T equal to square root of 3 B sub L, I sub L times power factor. This is in watts already, right? This is for a balanced three-phase load. So if we are given P total, we are given the line-to-line voltage, we are given the power factor, we could compute for I sub L. For I sub L now, okay, algebraic manipulation, it should be P total over square root of 3 B sub L times power factor. This formula here emanates from this, right? And the line-to-line voltage across the load is the line-to-line voltage specified in the problem, it's 460. So B sub L, the one needed in the formula is 460. P total should be the total kVA times power factor, that will be 600 kilowatts. So we now know P total, we now know B sub L, we now know power factor. The only unknown, no more unknowns, it's all given, right? So capital letter I with the subscript load, meaning the load current should be equal to 600, right, times 1000. This 1,000 here is what they call this a conversion factor. Because if P total is in kilowatts, we must have to multiply this by 1,000 watts per kilowatt. Okay, kilowatt cancel. So what remains on the unit of the numerator will be watts. So this 1,000 here is just a conversion factor. Over square root of 3, am I still on camera? Times 460 times 0.8. If you try to use your calculator, the total load current will be 841.33 amperes. So for a total load of 750 kVA, the total current on the secondary side is 841 amperes. It should be a very big current. Why it's a very big current? Big current, small voltage, right? On the primary side, big voltage, small current, right? So the load current consumed by 750 kVA, the magnitude of the current per line is 841.33 amperes. Okay? To compute for the primary current, we will be using this value here, and we will try to bring out the formula on how to compute for the ratio transformation using current values. The first one we use is by using the so-called voltage values. So by using the so-called current values, still ratio transformation will be I sub S over I sub P, closed quantity, subscript, phase value, for a step down. For a step down, the one on the numerator should be secondary current, and the one on the denominator should be the primary current with the subscript values. We will be using phase values, not line values. Okay? And the one being asked here is the primary phase value. If we try to compute for this, it will be IS over A. So this is, we computed IS over A. IS is actually, it's this one. The line currents are actually 841.33. And the secondary current being mentioned here is the current coming out from the windings. But since the connection is just series, okay, this is 841, so the secondary current should also be 841.43 amperes. It's balanced, right? We know the line load current already, so it will be the same as the phase current. Phase current meaning the current coming from the windings, right? So this will be 841.33 over the computed ratio transformation using the voltage values, which is 49.7. So this is over 49.7. So the phase current on the primary will be 18.94 amperes. Okay, you see the difference? The primary side is high voltage, the resulting current is small. So big voltage, small current. On the secondary side, small voltage, big current. Right? So the the problem is asking for the line current on the primary. Line current on the primary. What's the connection of the line current on the primary? It's delta, right? We computed this one already as 18.94, right? But that's why if we try to compute for the line current should be bigger because the connection is delta. And this line current is the vectorial sum of 18.94 plus this 18.94. If we try to compute it, okay, there's a relation, right? It should be by a factor of square root of 3. So the primary line current now will be square root of 3 times the computed phase value, which is 18.94, because the connection is delta. The line current should be bigger than the phase current by a factor of square root of 3. So what comes out is 32.8 amperes. So the line currents will be 32.8 amperes. Phase current will be 18.94 because since the connection is delta. Okay, you got it? Number 5, what is IS phase value? IS phase value, this one, the current coming from the windings on the secondary. Okay, all the currents on the secondary are all equal, right? The connection is just a pure series. It's not delta, right? So the secondary phase value equal to IL subscript load 841.33 amperes. Connection is Y. There is only one current value here, it's same as 841. The connection is Y. Number 6, the last requirement, primary phase current. Primary phase current, we computed that one already. It is 18.94 amperes, right? This one. Where's that one? It is this. Primary current phase value. The problem is asking for the primary phase current value. It's 18.94 amperes. Okay, that's it, guys. At least we now know how to relay voltages and currents for a delta connection, voltages and currents for a Y connection. Oh, this is the heart and soul of what we call this three-phase transformers. So when you take up your board exams, you will not get lost. Okay. Good evening from Los Angeles, Professor Epigene.